Okay, hello everyone. Let's start our lecture about general concepts on antennas. Let me begin by saying that when we have a communication system, we have two main methods for transferring the information, or let's say energy. One of them is use of transmission lines. So as you essentially connect one point to another with a transmission lines. So transmission lines comes in different form. For example, one of them is a two-wire transmission line. For example, let's say if this is point A, you connect it with a transmission line to point B. And we have other forms of transmission line. For example, we have coaxial cable. So you see, essentially, we have these two and these two conductors in this case. So this is our coaxial cable. And let me remind you about the concept of transmission line based on lump circuit theory. So when we talk about transmission line, the length of the transmission line is comparable to wavelengths, is not much smaller than wavelengths. So remember, in lump circuit theory, in what you had in basic circuit courses, what happens is that the size of the circuit is very small compared to wavelengths. But when we are dealing with antennas, radiating systems, and so on, we often talk about transmission lines. And these, in terms of lengths, are comparable to wavelengths. Let me make you an example. So imagine you are working at X band. The center frequency of X band is 10 gigahertz. So this is, let's say, this is the frequency that you are working. So what would be the wavelengths in air at 10 gigahertz? That would be velocity of light divided by f. Velocity of light is approximately 3 × 10⁸. Frequency is 10 gigahertz, 10 × 10⁹. So you end up with 0.03 meter or 3 centimeter. So that's the wavelengths that you have. Now imagine if I have just a two-wire system with the length of, let's say, 3 centimeter, which is very tiny. That's in fact a transmission line. So you cannot treat that as a lump based on lump circuit theory. For example, let me make you an example. Let's say if you have a 3 centimeter here, so let's make it a little bit different, maybe 4 centimeter. And now you have, of course, here open circuit, so nothing is connected to here. So this is, in fact, an open circuit. Now, if you go by lump circuit theory, for example, let's assume the frequency is very small. Then let's make an example. Let's say, for example, the frequency is 30 hertz. If frequency is 30 hertz, lambda becomes 3 × 10⁸. 30 hertz is 3 times 10. So you end up with 3 times 10⁷ meter. So this is essentially your wavelength. So of course, if you are dealing with 4 centimeter, this is so tiny. That's lump circuit theory. Now, if I tell you what sort of impedance you see from here, Z in, you would say, okay, this is open circuit, so this is just two pieces of wire. Of course, I see open circuit from here, and open circuit is impedance of infinity. So that's your transmission line, and that's your lump circuit model. If it's open circuit here, you connect with two wire, you see again open circuit. That was at 30 hertz, where wavelengths was so huge, 3 × 10⁷. Now, if I change the frequency, let's change the frequency to higher frequency, 10 gigahertz. So if I go to 10 gigahertz, now the wavelength is 3 centimeter. Now you're dealing with 4 centimeter. Now, if I ask you what is Z in here, if you immediately answer it's open circuit here, therefore it's open circuit here, that's wrong, because you are not using transmission line theory. You have to use transmission line theory in this case, because the size of the circuit, in this case, two-wire transmission line, is comparable to wavelengths. So remember, when the frequency goes up, then you are dealing with transmission lines in contrast to lump circuit theory. So you need to be careful. So in this case, you have to calculate that, and you're familiar with these from your previous courses, but still, I'm going to go over it when the time is right. But just to let you know that, again, at 30 hertz, this is exactly open circuit. When you go to 10 gigahertz, not anymore. So that's something that you should keep in mind. This is the definition of transmission line. So, and remember that in antennas, usually we are dealing with higher frequencies, like 10 gigahertz. So that's why transmission line become very relevant when we talk about antennas. So that was our transmission line. So we come back to it several times in the course. So something to keep in mind is that one method to transfer information from one point to another in communication systems would be transmission lines. The other one is to use electromagnetic radiation. So in this course, I'm usually say electromagnetic as EM. So EM radiation. So you're relying on electromagnetic radiation. In this case, then you don't need transmission line. For example, point A could be here, and point B could be here, somewhere else. And point B could be even in a space, for example. A could be on Earth. And then based on electromagnetic radiation, you create a communication system between them. You can communicate between these 2 points. So this is based on electromagnetic radiation, and this is gonna be the main topic of our course. And the tool to create electromagnetic radiation would be, in fact, antennas. So that's our course, ECE 4270, antennas. So to create electromagnetic radiation, we rely on antenna. We learn how to design the antenna to achieve desired electromagnetic radiation. Now, when we have electromagnetic radiation, let's see what is required for electromagnetic radiation. So what you require for electromagnetic radiation is accelerated charges. So you need to have accelerated charges. So if you have a charge moving with constant velocity, that's not going to give you electromagnetic radiation. You need accelerated charges. But then you might say, okay, in this course, we're not quite comfortable to use accelerated charge. We don't want to discuss at the charge level, perhaps. Then perhaps we can say, okay, accelerated charge is similar to saying time varying currents. So you essentially need to have time varying current. So you essentially need to have a current, like, for example, AC current, a current that's a function of time. So in other words, you're not going to be able to create electromagnetic radiation with DC current. You need time varying current. So that's one thing to keep in mind, that you need time varying currents. Now, as soon as I talk about time varying currents, I want to emphasize here that, as you'll see later on in the course, to have time varying current is a necessary condition. Sometimes you have time varying currents, but then you don't get radiation. Or maybe more appropriately, you don't get effective radiation. Look, let me make you an example. For example, imagine you have a transmission line. So you have your source, and this is connected to a transmission line. So starting from this point, and it has some length, and it goes to a load. So ZL. So the reason I'm saying this is transmission line is again because the length is comparable to wavelengths. So this is a transmission line that you have. Now, the source, let's assume the source maybe at 10 gigahertz. So the frequency is also high. Now, this is also AC currents in this case. Now, the currents that you're going to have in your transmission line is I as a function of T, because this is an AC source. Now, if you look at this system, this satisfies time varying current. In fact, this has time varying currents, but this is not an antenna. This is a transmission line. So to have antenna, you want to have time varying currents, but it's more than that. Now, I'm going to go back to this. I'm going to come back to this again. But let me briefly tell you here that, for example, in this case, the reason it doesn't become an antenna is that here you're going to have another current that can cancel the effect of this current when it comes to radiation. So when you are making an antenna, you need to design your time varying currents in an effective way. So if I want to mention something quickly here, then design of antenna is essentially design of the flow of currents in a way that gives you your desired radiation. So, so you might say, for example, for a certain radiation, you need two currents that look like that, two pieces of current that look like that. Now, what kind of a structure can give you something like this? That would be our discussion. So that's that's a little bit of introduction to communication system, two-type transmission lines and electromagnetic radiation. So now let's go a little bit into antennas and look at the antenna from system point of view. So usually what happens is that you have a source. This is usually what happens. You have a source, and then you have a transmission line. And remember, this transmission line I plotted long, but I'm just plotting it long to have a better representation. But in fact, this could be very tiny, because the only thing about transmission line is that it's comparable to wavelengths. Your wavelengths could be 3 millimeters. So a 3 millimeter line could be a transmission line. And then you go to antennas, for example. Now, if you look at this structure, what's going to happen here is that on this side, so right at the port of the antenna here, and this is where antenna goes to free space. So you see, antenna is almost like a transition device. So what is the transition between? So on this side, you have a transmission line. Now, transmission line guide electromagnetic waves. We call those waves guided waves because they're guided through the transmission line. So for example, you have plus charges here, for example, negative charges here. So, and then you have electric field like that. And then because it's time varying current, let's assume AC current, for example, then you might again have plus charges here, negative charges here, and have electric field like that. So you see, these electric fields are bounded between the two conductors. So these electric fields are bounded and guided along the transmission line. So this is your transmission line. So on this side, you have guided waves. So this is our guided waves. Now, what about on this side? What about on this side? On this side is different. Now, antenna gets our guided waves and transform them into free space wave, transform them into radiation. So when it comes to radiation, these are not bound by conductor. They're in free space. That's why I refer to them as free space waves. So what happens here is that it takes them, and now electric fields become, this has become your electric field. It's going to curl around itself, and it's going to be launched to the free space, and it can just travel. So you see, this is between guided waves and free space waves or radiation. And immediately you see here that these guided waves, they need these charges. These charges are maintaining these electric field. But here, when you launch these radiation into free space, then in free space, you don't have those charges to maintain them. But this is essentially the main thing of the antenna, that it relies on accelerated charges to create this radiation, but when it launches this radiation into free space, then these charges are not required anymore to maintain them. It's gonna go. So in summary, antenna is a transition device between guided waves and these free space waves. And if you want to think about Maxwell's equation, I want to a little bit remind you about Maxwell's equation here. In one of the Maxwell's equation that you learned in ECE 3580, tell you that divergence of D is equal to charge density. So I can write it as divergence of E equal the divergence of, maybe let me write D, which is electric flux density, as epsilon naught E equal charge density. And if epsilon naught is not a function of position, so it's let's say it's homogeneous, it's in free space, then you can take it out of divergence and it becomes rho divided by epsilon naught. Now, let's think about this equation. This equation says divergence of E is equal to charge density divided by permittivity of free space. If you remember, epsilon naught was permittivity of free space, 8.85, 10 to the power of minus 12 farad per meter. But that's not very important at this point. I want you to pay attention to this. What this equation tell you? This equation tell you that if you have a charge density which is positive, so it's a positive charge, then diverge, so let me just say positive, so rho is for positive charges, then of course divergence of E is greater than 0. If we are dealing with negative charges, rho becomes negative, divergence of E becomes smaller than 0. Now, what's the meaning of this? What's the meaning of divergence of E greater than 0? Divergence of E greater than 0 means E diverges from that point. Divergence positive means you are diverging from that point. Now, look at these positive charges here. We are diverging from them. So these electric fields are diverging from them. Now, look at the negative charge. If you have negative here, the divergence of E is negative. That means divergence is negative. That means you're converging. So that's why you're diverging from positive charges, but then you're converging on the negative charges. And now, if the positive charges are here, because that's an AC current, is a different cycle, then you are diverging from these positive charges, and then you are converging on these negative charges. So you see, this is very important in transmission line because these electric fields are bound between these charges. But now, when you go to here, when you are in free space, so the antenna created radiation for you, and now you're in free space. Now, here you don't have any charges. You don't have any charges. So what's going to happen? So your rho is essentially 0. So when your rho is essentially 0, that means divergence of 0. So here, as you see, there is no divergence here. So you don't see any divergence on this part because there is no charge when you go to free space by the antenna. Now, what you see here is the rotation of E. So I can remind you about a different Maxwell's equation, which says curl of E equal minus di B di T. So what happens here is that if you look at this loop, if we could see magnetic field here, we had magnetic field on this loop, and these magnetic fields that were passing through the loop like this. So imagine this was my magnetic field was passing through this loop. So this is my B. They were changing with respect to time. So for example, imagine it like this. I have now 2 pens. At one time instance, they were very strong to show B is strong. Now in a different time, B becomes smaller. It passed through this loop. So if B changes as a function of time, or magnetic field changes as a function of time, what's going to happen is that you're going to have curl of E, rotation of E. So this is essentially what's happening when it comes to this point. Now you're switching to curl of E minus di B di T. You see the effect of curl of E right there. So you see, this is a transition between these guided waves and this free space wave. So that's our antenna. So this is something that it's good to discuss it, and hopefully it becomes more and more clear when we go to more details about the antenna. Now, if we, for example, have another antenna at some other point, if we have another antenna at some other point, for example, somewhere here, so let's say in a different location on the Earth, you put another antenna here, and then you will receive this radiation and you give it to a load. So you start with guided waves, you use the antenna to go to free space waves. So now this is your transmitting antenna. Now you have this structure, which is your receiving antenna. Now it receives the energy from these radiation, and when it receives, it's going to create guided waves in this transmission line, and then you're going to feed your load here. So you see, you start from guided waves, you go to free space waves. These waves would be received by the receiving antenna, again converted to guided waves, and you're gonna have your load. So this is one situation that you could see. So that's so let's remember this, and I want to make an example that you understand divergence and curl a little bit better. It's not completely relevant to this, but it helps you to understand these divergence and curl. For example, let's consider, for example, so imagine this is, let's say it's a toilet bowl. So if you have a toilet bowl like that, then the water enters from here. So what happens here, if the water enters, so at this point, what can I say? Divergence is positive because the water is diverging from here. Now, when you flush, what's going to happen is that the water is going to rotate here. So I'm going to have this rotation, of course. So this is, I'm going to have a curl there, and then water is going to go in. So at this point, essentially, you are converging to this one. So you see here, we have somehow the effect of water diverging from a pipe, and then we have some rotation, and then again going to a different pipe. So this is not, there is no one-to-one correspondence here, but at least you can get the idea of divergence and curl a little bit better. So now this was our antenna. Now, when it comes to this structure, you see that I have a structure that in one side of it, I have my transmission line, and on the other side of it, I have my free space. Now, the first thing that we need to do with antennas, before learning how to design antennas, before learning some mathematical fundamentals of antennas, is to understand the parameters of the antenna. So what are the antenna parameters? So that's very important for us, and I'm going to tell you why. So antenna parameters are in fact extremely important for us. And the reason is that when you define antenna parameters, the important thing about the antenna, so you can understand antennas better and you can use the antenna more effectively. Now, when you see antenna has two sides, transmission line that's connected to a circuit and a space. Now, if I want to define parameters of antenna, I need to have two sets of parameters, one for the circuit side, the other one for the space side, right? So this is something unique about antenna. Now, let's consider, for example, the circuit size. So in circuit size, the most important antenna parameter is input impedance of the antenna. So this is extremely important, input impedance of the antenna. So why this is important? This is important because if you have a complicated antenna structure, but then this input impedance of the antenna tells you essentially you can remove this complicated antenna structure and you can replace the antenna from circuit viewpoint by an input impedance. So if you are communicating with a circuit engineer, then the only thing that person needs to know about your antenna is the input impedance of the antenna. So this is essentially tells you that circuit people can remove this antenna completely. So they have their source and whatever complicated structure that they have, and then they model the antenna by an input impedance ZA, which is a complex number in general. So that's extremely powerful. Let me, for example, show you one antenna that I have here. So this is an antenna that we have. It's a horn antenna. You're going to be looking at that in the measurement video labs that I made. This is from a LabVolt training antenna system. So you see, imagine this is connected to a circuit. So, and this is the connection port. So this thing here is the connection port. So you connect with a coaxial cable to this. Now, this structure is a complicated structure. Now, how can a circuit engineer can use this? So it's very complicated. So what would you do? So you essentially say, if I look at the antenna from its excitation port, which is here, it looks like an input, essentially an input impedance, a complex number. So you're going to remove this, and I'm just going to use the value of the input impedance. That's extremely powerful because then you don't need to go to the details of the antenna. That's another antenna again by in our measurement lab. So this is a microstrip antenna. So you see this has different components, but then excitation port here. Now, if you connect this to a circuit from circuit viewpoint, you can remove the antenna completely and assume that you have a load with a certain input impedance here. That's extremely important and such a powerful concept. So this would be our input impedance of the antenna. We have other parameters here that I'm going to talk about them. For example, we have different things like radiation efficiency, VSWR. Let me, for example, write that stands for voltage standing wave ratio and so on. But when we go to free space, we have also very important parameters here. Perhaps the most important one is we need to know the radiation pattern of the antenna. So this is something that we actually do a lot in our measurement lab, which we measure radiation pattern of the antenna. So for example, if you look at this dipole antenna that we do measure in our lab, so we'd like to know that, for example, does it radiate more here toward this direction or more toward this direction? So this is the radiation pattern. So you give some power to this antenna, and this antenna is going to radiate this power. If, for example, you give 1 watt, it's going to take this 1 watt and radiate it into different directions. So some of the directions are favored direction. It radiates more toward that direction, radiate less in some direction. So this is the radiation pattern of the antenna. You should know that. Sometimes you want to have, for example, you want to have your maximum radiation towards certain angle, let's say theta equal 20. Sometimes you get interference from another direction and you don't want to receive from that direction, which is equivalent to saying you don't want to radiate to that direction. So in that case, you want to create a null in that direction. So these are all radiation pattern. So, and then radiation pattern can be more quantitative, so you can get associate meaningful numbers to radiation pattern, and that brings us to gain of the antenna, directivity of the antenna, uh, and then also you've learned about polarization of the antenna. We're gonna in your ECE 3590. So we're gonna talk about also polarization and so on. So you see, we have a set of parameters on this side. We also have a set of parameters on the other side, and we need to cover all of them. So that would be the first part of the course. We're gonna talk about antenna parameters. After we're done with antenna parameters, I'm going to go through a couple of mathematical things to get to one important equation. And based on that equation, I'm going to justify our design philosophy for antenna. And then we're going to go over different antenna types like dipoles, loops, monopoles, microstrip antenna, horn antenna, reflector antennas, and so on. But for now, let's understand the important parameters of the antenna. So let's start with this thing, which, as I said, is extremely important when it comes to antenna from circuit viewpoint. So let's talk about this one. Okay, so essentially what I said was that if you have an antenna like this, and this is the excitation port of the antenna where you bring the energy to the antenna using this port, you can remove this antenna from circuit viewpoint, and at this point you represent the antenna with a complex number, which is the input impedance of the antenna, and we refer to that as ZA, and I'm going to write it as R plus JX. So this is a complex number. R is its real part, X is its imaginary part. Now, my question here is that what does R represent? So let's focus on R and see what does R represent for us. What is R? Now, if I ask you this question, if you are just into circuit, you immediately answer me. Let me make you an example. For example, imagine I have a circuit like this, and I tell you what is the input impedance here. You say, okay, this is R, this is L, then you say R plus J omega L. So if you compare this with that, you say R, X is omega L. So you have resistance, you have inductance here. So then you would say, okay, resistance is the loss of energy. So you may guess that this R is the loss of energy. So in that case, you might say, okay, the real part of the input impedance of the antenna is loss of the energy. So is that correct or not? It is correct, and also it is incorrect. But you need to be very careful. Yes, R represents the loss of the energy, but it's a little bit different than this loss. It's the loss of the energy from the circuit viewpoint. So circuit feels that circuit has lost some power. So this is from the circuit viewpoint. Now, how can you lose some power? So one way is through resistance. So it would be converted, for example, to thermal energy. So you will lose some power. So basic resistance in circuit. So that would be loss of energy. But in antenna, we have another mechanism for loss of energy. Imagine this is connected to a circuit. So this is the port, and this is connected to a circuit. So you're bringing power to the antenna. Now, this antenna consists of some metals. So of course, you're going to lose some power because this is not perfect electric conduct. You're gonna lose some power because of conduction loss, for example. It's not perfect electric conductor. It's like a non-ideal metal. But remember that part of the energy, antenna is going to turn it into radiation. So that's the job of the antenna. So if antenna radiates part of the energy, so what's going to happen is that from the circuit viewpoint, that energy has been lost because has been radiated away. So that's the loss of the energy from circuit viewpoint. So remember, that energy has not been wasted. It has been transferred into radiation. But from circuit viewpoint, circuit doesn't know that. Circuit says, okay, for example, I gave this device 1 watt and I don't have that 1 watt. So when you have the real part, yes, that's the loss of energy from circuit viewpoint, but it's not waste of energy in this case. So this R in antenna consists of 2 parts. One of them is conduction or dielectric, conductive or dielectric loss, which is a bad thing. For example, let me make you another example. This is an antenna that we call patch antenna. Now, this antenna consists of metal, and also there is a thickness here that's dielectric. So if the dielectric is not ideal, I'm going to have dielectric loss. If the metals are not ideal, I'm going to have this conductive loss. So this is something that's bad for me. But then I'm going to radiate some of the energy into a space. It's going to be electromagnetic radiation. That's something that I consider good. So, and that's my radiation. So this would be radiation. And I call this component radiation resistance, which is a good thing. So this is, I'm going to denote it by R, subscript R, and I'm going to denote this by R subscript L. It stands for loss. So this is radiation resistance. This is the loss. So R of the antenna consists of 2 parts, RR plus RL. So this is something that you should keep in mind, that this is not waste of energy all the time. This would be our waste. Now, this is our radiation resistance. This is our loss. And now, based on this, we have an important parameter called radiation efficiency. And is defined as the ratio of RR divided by RR plus RL. That's our radiation efficiency. So you see, that's the total R, and the numerator you have only the radiation resistance. So that would be the radiation efficiency of the antenna. For example, if you don't have any loss, so RL would be 0, and RR divided by RR would be 1. So therefore, you have radiation efficiency of 1, but we usually present it in terms of percentage. Instead of saying if RL is 0, it's 1, we say 100%. Or let's make another example. Let's assume that radiation efficiency, for example, in one case is 0.5. How do you usually present that? You say 50%. And sometimes you present it in dB. So if you want to present it in dB, you take 10 log of base 10 of the number, which is 0.5, and then you end up with minus 3 dB. So you say radiation efficiency is 0.5 or 50% or minus 3 dB. So this is your radiation efficiency. Something about this radiation efficiency that I want you to know is that this is very simple. It's just this divided by that. But don't think that this is easy to find in practice, because what you can measure, so we have a device called vector network analyzer. We can connect the antenna to the vector network analyzer, and I'm going to show it to you later. And when you connect your antenna to the vector network analyzer is going to give you this number. So let me write it here. You already seen this device in other courses. So we usually call it VNA. So when you connect this to VNA, it gives you this number. But then VNA doesn't give you RR and RL. It just gives you R. So you essentially have this number, but you don't know RR. So there are procedures to find that, but that's not very easy. So radiation efficiency in terms of equation is easy, but in terms of measuring it, it's not very easy. So, and there are methods to find it, but just wanted that you know that having R is straightforward, not these two separately. So this is our R. Now, what is our JX? So I want to again bring you back to this basic circuit thing that I have here. What is the meaning of L? L essentially creates a stored energy for us. So this is the stored energy. So, or reactive energy. So this RR correspond to radiative energy. So the energy that's radiating. So this is radiative energy. But when you have the imaginary part of the input impedance, that has to do with the stored energy. So you're storing the energy around this. So if the antenna has the J part, that means if this is my antenna, some of the energy is going to go away. So it's going to radiating away. But if I have Jx for the input impedance, that means I'm storing energy around the antenna as well. So you're also storing the energy similar to inductor, or you might change it with, for example, if this is like that, then if you look at this, this becomes R plus 1 divided by J omega C. You can bring J to the numerator, and this becomes R plus J minus 1 omega C. So you see, again, you have a J part, but this time is negative times J. This is positive times J. Both of them are a stored energy. So this is capacitive, this is inductive. So if you have a JX for the antenna, that essentially means you are storing the energy around the antenna. This is usually not something good, because this device is not for storage. It's for radiating away. So that's why this JX, we need to try to bring it as close as possible to zero in most cases. And that's what we usually refer to resonance. So if that happens, then we say this is at resonance. So that means this X goes to zero. For example, in the first simulation lab, you see that we start with a dipole antenna, and that dipole antenna has some JX. So you're going to see that, for example, if you start with an antenna, you have this as, for example, something like this, for example. So we have an antenna with this input impedance, so 73 J42. So now if you look at that, this 73 is a combination of RR and RL. For that particular antenna that we study, that we will study in the simulation lab, RL is negligible, is nothing. So this 73 has to do with the good thing, RR. But then this J42, that means your antenna is storing energy around itself. So when it's storing energy, that's not a good thing for our application, because we want to send the energy away. So we want to minimize that. So we play with the antenna a little bit. Specifically in that example, we're going to play with the length of the antenna a little bit to bring that J42 very close to zero, so that this becomes almost 73. Now we say, okay, the antenna is at resonance. So that would be something that's important for our application. So remember that this is essentially the stored energy, which corresponds to reactive energy. So that's for essentially the main aspect of the main points about input impedance. Something else that I want to also mention is that now that we talked about transmission line and so on, it's also good to remind you about the input impedance seen from a transmission line. For example, if you have an antenna with the input impedance of ZA, and this is a transmission line that you have, and this transmission line has a characteristic impedance Z0. It has wave number beta and length L. So this is your length L, wave number beta, Z0 is your characteristic impedance. So these are, I'm going to also talk about characteristic impedance in more details, but for now, I assume that you already know that transmission line has a main property, which is its characteristic impedance, wave number and L. So now if I ask you what is Z in from here, then this would be like something that you need to be able to calculate. Now, if you forget about transmission line, you just say, okay, this is two pieces of wire, this is ZA, so if this is ZA, this is ZA2. That's wrong. That's for lumped circuit theory, where these two wires have no effect. But here we are talking about transmission line, so we need to be able to calculate Z in, considering that this is a transmission line. That means this length is comparable to wavelengths. So the equation that for Z in would be equal to Z0 plus J, Z of the antenna, tangent beta L, Z of the antenna plus J Z0 tangent beta L. So this would be Z in. As you see, it depends on the characteristic impedance of your transmission line Z0. It depends on the impedance of the antenna. In the previous courses, when you had this, ZA was ZL, load. But here I wrote it as Z subscript A. And beta, wave number, and length L, length of the transmission line. So this is Z in, and in some cases, you need to be, I'm going to ask you to calculate that. Something about this, which is a good practice that I show you, is that I want to show you that this essentially becomes like lump circuit theory when the length of the transmission line is small. To see that, let me remind you that beta is 2 pi divided by wavelengths. So beta L is 2 pi divided by wavelengths times L. Now, remember that F equal 30 hertz example that I made? Lambda was so huge, 10 to the power of 7. So imagine your length is tiny, 3 centimeter. So 3 centimeter is 3 10 to the power of minus 2 divided by 3 10 to the power of 7. This is extremely tiny. So tangent of a tiny angle is 0. So if length is much smaller than lambda, tangent of beta L goes to 0. Now, if tangent of beta L goes to 0, what would be your Z in? Becomes Z0, Z0 plus 0, then ZA plus 0. These two become 0, and then Z0 and Z0 cancel. You get ZA. So you see, as you expect, if lengths is much smaller than wavelengths, this becomes lumped circuit. Therefore, Z in from here is essentially ZA. But in antenna theory, we don't satisfy that. We always in a situation that the frequency is high and we're dealing with transmission line. So you need to use this very important equation. Just one quick comment about this equation. This equation is for lossless transmission line. So if the transmission is lossy, it's a bit different. But in examples that we're going to cover in this course, we always assume that transmission line have a small losses. So we're going to be using this equation for our cases. But more general, you need to use the equation that also incorporates the loss within this transmission line. Okay, so this is our discussion on the input impedance of the antenna.